Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a Calculus 1 lecture. I hope you enjoy it. This is Chapter 3, Section 6, so 3.6, which is derivatives of inverse functions. All right, here we go. So first, let's start with a theorem. That's a theorem. All right, and this is for continuity and differentiability of inverse functions. And this is what it says. All right, it says let f be a function, all right, whose domain is some interval I. All right, so we have a function with a domain. All right, if f has an inverse function, on that interval, then the following are true. This is true. So the first thing is if f is continuous on its domain, that interval I, if f is continuous on I, then f inverse is continuous on its domain. So by that we mean on its own domain, right? On the domain of f inverse. So if f is continuous on I, right, I being the domain of f, so if f is continuous on its own domain, then f inverse is also continuous on its own domain. The next thing, if f is differentiable, and I'm going to abbreviate differentiable with diffable. So if f is differentiable on an interval containing c, then f, and f prime of c is not equal to 0, then f inverse is differentiable at f of c. All right. All right. So let's get a visual to this, but first let's think about this. So we're saying we have a function f, right? And that function f. So right now we're talking about the first point. We're talking about this. So this function f, right? That function f is continuous. So the fact that it's continuous is going to tell us that its inverse is also continuous. Okay. This thing is telling us, well, the second point here is that if f is differentiable, right, at some point, and f prime at that point, in other words, its derivative at that point is not 0, then f inverse is differentiable at f of c. So let's see what we're talking about there. All right, so let's get a visual. So before I do this visual, let's recall. Well, let's do this. So let's say that this right now is f of x. All right, something like this. Let's say this is f of x. All right, and let's say, well, one thing to recall about a function and its inverse is that they're symmetrical about the line y equals x. So here, this dotted line is y equals x. All right, and since they're symmetrical about that point, well, this is what f inverse is going to look like. So something like this. All right. Something like that. All right. So that in blue, that would be our inverse, f inverse of x. So what we're saying here is, and I'll do this part in red. What we're saying in this number 2 is saying, well, f is differentiable at some point, right? F is differentiable. So what does that really mean? And let's use a different color here. Let's use this purple. Let's say that this point right here is at C with the height of f of C. All right. So at this point, well, a tangent line exists, right? So a tangent line exists. So in here, it's the function is differentiable, right? Because the tangent line is not 0. I mean, the slope of the tangent line is not undefined, and more importantly, it is not 0. Why do we care that it's not 0? Well, for the next part over here, the f inverse is differentiable there too. So what do we mean by that one? And let's see, let's use green. Well, if there's a point here in f of x, well, there's also a point over here at f inverse of x, and that point is at, well, where the functions and their inverses, the domains and range change. So where this was at, there where this x value was c, well, now that's the y value, and where this y value was f of c, well, now that's the x value. And here, this is also gonna have a tangent line, all right? And this in here, this is implied that it exists based because of the fact that this one exists. That's what this is telling us, all right? The fact that in our function f, we know that a slope exists there, and it's not equal to 0. That slope is not equal to 0. Well, then on its inverse of the function over here, that will also have a slope, right? That's essentially what this is telling us. Now, how do we find that slope is the question. So in here, what we're going to look at is, well, given some function of x, how can I find this value over here without ever finding what f of inverse is? All right, that's what we're going to look at. We're not even going to ever solve for f inverse, but we can still figure out what's going on with it over here. All right, so for example, actually, let's do a theorem. So the theorem that tells us how to do this. So theorem. The derivative of an inverse function. All right. So let f be a function that is differentiable on some interval I. If f has an inverse function g, all right, so we're going to call the inverse function g, then g is differentiable at any x for which f prime of g of x is not equal to 0, all right? Moreover, g prime of x is 1 over f prime of g of x, right? And again, that's as long as f prime of g of x is not equal to 0, all right? So in here, let's see what this says. It says if f has an inverse function g, then G is differentiable at any x. All right, we kind of knew that already because that's what we hear was implied between 1 and 2. All right, especially number 2. So if f is differentiable, then G, its inverse, is also differentiable. Okay, cool. Now, this is telling us that the derivative of the inverse function is 1 over the derivative of the original function. All right, that's essentially what this is telling us. Now let's put this in terms of inverses. All right, so if g of x is equal to f inverse of x, then g prime of x will be the derivative with respect to x of f inverse of x. So now what we can say here is that this statement really becomes the derivative with respect to x of f inverse of x is 1 over f prime of f inverse of x. All right, and this is as long as f prime of f inverse of x is not equal to 0. All right, let's do a proof for this statement real quick because it is a very quick proof. So if I have a function and its inverse, recall that if I have a function and its inverse and I compose them with each other, I'm supposed to get just x, right? That's just a definition of inverse, a function and its inverse. Now, if I take the derivative of both sides, well, I end up with, well, using the chain rule, f prime of f inverse of x times the derivative of the inside, the derivative of f inverse of x. And on the right side, the derivative of x is just 1. So at this point, dividing this into the other side, I get the derivative with respect to x of f inverse of x is 1 over f prime of f inverse of x. All right. So that's our proof there. Now let's do an example here. All right, let's do an example to find this. So example A. Let f of x be equal to x cubed plus 2x minus 1. All right. So we're going to find a few things. All right. The first thing we're going to say is, well, what is f of 1? All right. And, well, what are we going to do? Well, this is just telling us plug in 1. So we have 1 cubed plus 2 times 1 minus 1. So that's 1 plus 2 minus 1. So that's equal to. So that what did we find here? We found the point 1, 2. Right? When I plug in 1, I get 2. X comma f of x. All right? Cool. So next question. What is f inverse of 2? Well, let's think about that for a second. All right, and let's think about that over here. If I have the point x, well, let's do it this way. Let's say here's x. Here is f of x, right? And we go from x to f of x via the function f. And then to go the other way, we go with f inverse, right? So what does that tell me? That when I plug in x here, I end up with f of x over there. But if I plug in f of x, I end up with x. How is that useful? Well, when I plug in x, I end up with f of x. And when I plug in this value into the inverse, I end up with that value. So right away here, I know that f inverse of 2 is 1. Okay. The next thing, let's find what f prime of x is. F prime of x would be 3x squared plus 2, right? Now let's figure out what f prime of 1 is. Well, that would be 3 times 1 squared plus 2. So that's 3 plus 2, which is 5. Cool. Now, let's really figure out the new stuff here. Let's do the derivative with respect to x of f inverse of x. But we want to evaluate this at that specific point, right? So we want to evaluate this at 2, all right? Because that's what we're plugging into f inverse 2. So in here, let's make that a 2. All right. Well, we know by our definition up here that it's just 1 over f prime of f inverse of x. So it's 1 over f prime of f inverse of 2, right? All I did there was apply this formula up here. So what does that give me now? Well, f inverse of 2. We already know what f inverse of 2 was. F inverse of 2 is 1. So here I got 1 over f prime of 1. And then f prime of 1. F prime of 1, we already solved for that. That's 5, so I get 1/5. All right. So there we go. We found f inverse of, we found the derivative of f inverse of 2. All right. So let's see visually, what did we just find? Okay. So here is our x and y chart, or x and y plane, I should be saying. And let's say, well, so our function here, I'll draw in yellow, all right, and it looks something like this, all right. That's essentially what the function looks like. I'll draw in here in red. Ooh, that's not what I meant to do. What was that? There we go. This in red is our line y equals x, all right. And you'll see in a second why I'm drawing that. In here, we've got this point, all right? We've got a point of 1, 2. So here at 1, we're at the height of 2, all right? And what did we find here? We found that f prime of 1 is 5. Okay, what does that mean? That means that at the tangent line here, we've got a slope of 5. Well, let's draw this tangent line better. That's kind of better. All right, so in there, that has a slope of 5. So that in yellow again was f of x. Now, in purple, let's look at what f inverse of x looks like. Well, again, they're mirror images about that line y equals x. So it's going to look something like this. All right. And what we see here is that, well, this point 1, 2 existed on f of x. Maybe I'll change where the position of that. That point 1, 2 is on f of x right here, right? Well, the point 2, 1 is going to be on, so the point 2, 1, well, actually should have been, let's draw it here. This is not drawn to scale, right? So let's say that's 2. Ooh, now what I meant to do. That's the point 2, 1. Ooh. And here, at that point 2, 1, we're going to have a tangent line. Okay. And we found there is that the slope of that tangent line is 1/5. And there in purple, that was f inverse of x. But notice that I never solved for f inverse of x. We have f of x cubed plus 2x minus 1, but I never solved for its inverse. All I did was use the properties there to figure out what the slope was at that point over here on the inverse function, but I never figured out what f of inverse was. Let's do another one. B. So let's say that I have f of x being equal to sine of x, all right? And because we want this to have an inverse, we're gonna restrict its domain to be from negative pi over 2 to pi over 2. All right. So now let's see what we're gonna find here. We're gonna find f of pi over 6. We're also gonna find f inverse of 1/2. We're gonna find f prime of pi over 6, and we're also going to find d dx of f inverse of 1/2. All right, so let's take this one at a time. So we're going to say f of pi over 6. F of pi over 6, well, that's just saying sine of pi over 6. Sine of pi over 6 is 1/2. Okay, next thing, f inverse of 1/2. F inverse of 1/2. Well, in here, recall that this is telling us that we have the point 1/2 comma, wait, sorry, I messed that up. We have the point pi over 6 comma 1/2, right? Our input is x, our output is y. So going from here to here, that was going via the function f. So going backwards, that's the f inverse function. So f inverse of 1/2 pi over 6. All right, the next thing, I need f prime of pi over 6. Well, before that, I need f prime of x. And our function was sine. So the derivative of sine is cosine of x. All right, and we want f prime of pi over 6. So f prime of pi over 6, that's going to be cosine of pi over 6, which is radical 3 over 2. All right, the next thing, the last thing that we want here is this part, f inverse at its derivative. Okay, so first let's recall what the derivative of f inverse was. The derivative of f inverse is 1 over f prime of f inverse of x. So if I'm asking for the derivative with respect to x of f inverse of 1/2, that means 1 over f prime of f inverse of 1/2, which, well, f inverse of 1/2, that's pi over 6. So I have 1 over f prime of pi over 6. F prime of pi over 6, that's radical 3 over 2. So I have 1 over radical 3 over 2. But in here, this is saying 1 divided by a fraction, which really means multiplied by the reciprocal, which is how I get 2 over radical 3. But we don't like radicals in the denominator, so we're just going to rationalize this to get 2 radical 3 over 3. All right, and in there, I just found the slope on the inverse function. All right, now let's move on from that idea. Let's just in general talk a little bit more about some other inverse functions. All right, so let's say that I had to find dy dx. Find dy dx. And here I'm going to say y is equal to arctan of x. All right? Y is equal to arctan of x. Now, I sort of already did something like this in 3.5, but I want to explore this a little bit more. If I take the tangent of both sides, I end up with tan of y is equal to x. If I take the derivative of both sides, well, I get that side is equal to 1. On this side, the derivative of tangent is secant squared, but then by implicit differentiation, I end up with dy dx. So at this point, this tells me that dy dx is 1 over secant squared of y. But recall that tan squared theta plus 1 is equal to secant squared theta. So in here, this is really saying 1 over tan squared of y plus 1. But we already knew what tan y was. Tan of y was x. So here I have 1 over x squared plus 1. So what did we find here? Well, what we found here is that the derivative with respect to x of arctan of x is 1 over x squared plus 1. All right. So there we go. Now we know what the derivative of arctan was. So let's go ahead and talk about all the derivatives of the inverse trig functions. So theorem. Derivatives of inverse trig functions. All right. So let u be a differentiable function of x. All right. Then the derivative with respect to x of arcsine of u would be 1 over the square root of 1 minus u squared times u prime. All right. Let's shift that over a little bit. That's the derivative of arcsine. Now the derivative of arccosine of u. The derivative of arccosine of u is negative 1 over the square root of 1 minus u squared times u prime. The derivative of arctan of u, well, we just kind of figure that one out. It'll be 1 over u squared plus 1, but then because of the chain rule, times u prime. The derivative with respect to x of arc cosecant of u would be negative 1 over the absolute value of u times the square root of u squared minus 1 times u prime. The derivative with respect to x of arcsecant of u is 1 over the absolute value of u, square root of u squared minus 1 times the u prime. And lastly, the derivative with respect to x of arc cotangent of u would be 1 over, negative 1 over u squared plus 1 times u prime. All right. So those are the derivatives of the inverse trig functions. All right. And now again, as to why that would be, well, again in the previous section, I showed why arcsine becomes that. And here we just show the arctan. All right. But as far as all the other ones, same exact kind of trick applies. So even if you don't memorize these, you can always figure them out by applying something like what I did up here in this example. I do highly recommend that you do memorize these, all right, as they will come around in general throughout your calculus career. So the more of these derivatives that you do memorize, the better. But even if you don't memorize it, again, as long as you remember how to actually find it out, it should be fine enough. So let's go ahead and do some examples. So example D. So let y be equal to, let's start with sine inverse of 4x, right? So then, well, what would its derivative be? Well, then dy dx would be, well, let's look at the formula. It was 1 over the square root of 1 minus u squared. Okay, this is our u. So we have 1 over the square root of 1 minus u squared, and again our u was 4x, times u prime, the derivative of the inside, that's by chain rule. So in here times 4. So what we really get here is 4 over radical 1 minus 16x squared. All right. Next one, e. Let's say I had f of x is equal to tan inverse of 2x cubed, right? So then, well, what would f prime be? Well, f prime, its derivative would be, well, let's again look at the formula for tangent. 1 over u squared plus 1 times u prime, all right? 1 over u squared plus 1. And here, this is our u. So we have 1 over u squared plus 1, and our u was 2x cubed, times the derivative of the inside by chain rule, so times 6x squared. So this gives us 6x squared over 2 squared, that's 4, x cubed squared is x to the 6th, so 4x to the 6th plus 1. All right, so that's E. F. Let's say that I have y is equal to cosine inverse of, let's do x squared plus 2x minus 1 to the 1/2. All right, so I have cosine inverse of that. So let's see what this gives us. Well, this entire thing is our u, right? That entire thing is our u. So by the formula up here, for our cosine, negative 1 over 1 minus u squared, square rooted, okay? So we have that dy dx, negative 1 over the square root of 1 minus u squared. And what was our u? This entire thing here. So we have x squared plus 2x minus 1 to the 1/2. All right. And then by chain rule times the derivative of the inside. Well, what is the inside here? So we need to take the derivative of this piece. So we have 1/2 times x squared plus 2x minus 1 to the negative 1/2 times, well, by the chain rule, the derivative of that inside. So times 2x plus 2, right? Notice here that 2x plus 2 is really just 2 times x plus 1, all right? And I bring that up because we have a 2 here and a 1/2, so those two cancel each other out. So what do we really have here? What we've got here is that dy dx is equal to the negative of x plus 1 over, and here we've got the square root of 1 minus to the 1/2 squared. Well, those two cancel each other out, so I have x squared plus 2x minus 1. And then we have this times, well, on the bottom, we still have all of this, right? I'm going to bring this down to the bottom with a positive exponent. So I can just say x squared plus 2x minus 1. All right. There's not really that much else that we can do here, so I'm going to end it at that. But if we really wanted to, we can go further, right? I'll go one step further. In here, if I distribute this negative, so I end up with 1 minus x squared minus 2x plus 1. 1 plus 1 is 2, so we really have here, I'll write it as 2 minus 2x minus x squared. And that's inside the radical, right? So what does that give me? Over here, I'm going to write it as the negative of x plus 1 over, notice that both of these have radical signs on them, so I'm just going to say the radical of 2 minus 2x minus x squared times x squared plus 2x minus 1. All right, I'll leave it as that. There's no point in going any further. All right, but I would have said it would be fine if you stop here. All right. All right, so that was F. G. Let's say that we had that I asked for the derivative with respect to x of cosecant inverse of e to the 2x. All right. Well, what does cosecant inverse look like? What is the derivative? Well, here we go. I'm gonna go ahead and copy and paste that so that we can keep that in the back of our heads when we go down here. All right. And I'll put it in blue because it's side work. All right, cool. Now, in here, let's apply that. So in here, the derivative is going to give us, well, based on this formula, we're going to say this is, our u is e to the 2x, right? So I have negative 1 over absolute value of u, so absolute value of e to the 2x, times the square root of u squared, so e to the 2x squared, minus 1, times u prime, so the derivative of e to the x, so that's 2e to the 2x, right? This 2 came from the chain rule, right? So in here, let's see what we have. Let's note something here. Let's look at this absolute value of e to the 2x. E to the 2x is greater than 0 for all x, right? In general, all exponentials, unless we have anything else over here, an exponential is always positive, right? Anything in the form a to the x is positive for a being greater than 1. Actually, it's true for a being greater than 0, but in general, it's true, right? So this is positive for all x. Why do I care about that? Well, because in here, we don't really need this absolute values anymore, right? So now this absolute values go away, so this is going to get to cancel with that. So what I end up with here is just negative 2 over the square root of e to the 4x, right? Because 2x times 2 is 4. So e to the 4x minus 1. All right. Next one, h. Let's say that h of t were equal to sine of arc cosine of t. All right. So here we go. Well, h prime of t. The derivative of sine is cosine, so we get cosine of arc cosine of t. But then by chain rule times the derivative of the inside, the derivative of arc cosine. Well, we just did that, but let me remind you what it was. It was negative 1 over, where is it? The square root, here it is. Negative 1 over the square root of 1 minus u squared. So in here, it's going to be negative 1 over the square root of 1 minus, well, we were working with t, so 1 minus t squared, all right? And in here, cosine of arc cosine. Cosine of arc cosine, well, those are inverse functions, so they cancel each other out, so I just get t out of this entire thing. Well, maybe I'll do that in a different color to not be confusing. So this entire thing is just t. So I end up here with just negative t over the square root of 1 minus t squared. All right. Now, there's another way of doing this problem. All right. Let's look at that. Now, I personally do recommend that you do it this way, but I do want to show you the alternative to doing this kind of problem. All right. So I'll do this in yellow to signify that it's the alternative, right? To h, so asterisk, all right? So h of t, we said it was sine of or cosine of t. All right. So the alternative is to rewrite this function. All right. And how do we do that? Well, recall that for sine, the inputs are all angles. So let's say that theta is equal to arc cosine of t, right? Because it's an angle. If I take cosine on both sides, I end up with cosine of theta is equal to t, right? And let's figure out what this. Maybe I'll do that part in blue, or this part. So let's figure out what this implies. All right. If you recall from pre-calc, all right, this cosine of theta equals t. It implies a triangle. All right. If this is theta, well, from SOHCAHTOA, cosine of theta is adjacent over hypotenuse, right? That's our one. Meaning that this side over here by the Pythagorean theorem is the square root of 1 minus t squared. All right, that's from the Pythagorean theorem. So what would sine theta be? Well, in here, right, because theta is our cosine of t, so this tells us now that sine theta is, well, from SOHCAHTOA, opposite over hypotenuse. Opposite over hypotenuse. So I have the square root of 1 minus t squared. So essentially, what we can say now is that h of t is really just 1 minus t squared to the 1/2. So its derivative, h prime of t, would be, well, let's apply the chain rule. 1/2 times 1 minus t squared to the negative 1/2 times the derivative of the inside, so times negative 2t. At that point, this 1/2 and these 2 cancel each other out. This negative exponent goes to the bottom, so I end up with negative t over 1 minus t squared to the 1/2. And look at that. That's the same exact answer that we had over here, right? This radical sign is just the same thing as saying to the 1/2, right? So 1 minus t squared to the 1/2. So two different methods, very different methods, but still getting to the same answer. All right. Now in this version up here, we did it by memorizing what the derivative of arc cosine is. In this method down here, we did it by recalling some cool tricks from pre-calc, right? Recalling some how to manipulate these kinds of functions. All right. So that's the only one that I'll do that way. Next one. Perhaps I'll do one more like this. So let's say that I have f of x is equal to tangent of cosecant inverse of, I don't know, let's do 3x squared. All right, so in here, what we're gonna do is we're gonna, well, first have correct notation. All right, so we're gonna take the derivative in the first way that I did it, right? In this version over here, like in white. All right, so in here the derivative, well, I have f prime of x is going to be, well, the derivative of tangent is secant squared, and then we have here cosecant inverse of 3x squared times the derivative of the inside. The derivative of cosecant inverse, well, let's see what it was. It was, there it is, -1. I'm looking at this over here, so I'm going to go ahead and copy and paste that and put it right here. All right, and I'll put it in blue. All right, so it's -1, and let's write in white, -1 over the absolute value of u, the inside, so the absolute value of 3x squared, times the square root of 3x squared minus 1, right? That's our u. And then times u prime. Well, the derivative of 3x squared is 6x. All right. Now, in here, Um, Notice that in this one, this part doesn't cancel out as easily as the previous example did, right? So the question is, what do we do with that? Well, in here, we'd be forced to come up with those triangles again anyway, like the triangle that this piece implies. So if I say theta is equal to cosecant inverse of 3x squared, that tells me that cosecant theta is equal to 3x squared. Now, why do I care about that? Well, from SOHCAHTOA, well, cosecant isn't in there, but I know that sine is. So cosecant is 1 over sine. So that tells me now that sine, if I take the reciprocal of both sides here, sine is equal to 1 over 3x squared. And that implies this triangle. If this is theta, sine is opposite over hypotenuse, right? Opposite over hypotenuse, meaning that this remaining side here would be the square root of 3x squared minus 1, right? So from there, now I can figure out what secant of that is. So I can figure out secant squared. So secant theta. So secant is 1 over cosine, right? The reciprocal of cosine. And from SOHCAHTOA, cosine was adjacent over hypotenuse. So the reciprocal would be hypotenuse over adjacent. And 3x squared is really 9x to the 4th. So that minus 1, right? So that was hypotenuse over adjacent. So what we really get here is, well, that's secant, which implies that secant squared would be, well, this entire thing squared, meaning 9x to the 4th over 9x to the 4th minus 1, right? Because the square root squared, it goes away. So what do we find here? Well, now let's go ahead and simplify our f prime. So f prime of x was, well, what was it? It was secant squared. Well, secant squared we just figured out was 9x to the 4th over 9x to the 4th minus 1. So that's secant squared times negative 1 over that stuff. All right, so we have negative 6x over, notice the absolute value of 3x squared. Well, for all values of x, that's at least 0, right? So because it's irrelevant of what I plug in for x, right? Because I'm squaring it, it's always going to be positive. So in here, we can just go ahead and ignore the absolute value signs and write 3x squared. And then we have times the square root of 9x to the 4th minus 1, right? This part right here. So, I mean, if we really wanted to keep going a little bit and simplifying this a little bit more, well, this is all being multiplied, right? Well, let's see what we can do. This 3 reduces with this 6, it makes it a 2. This x squared reduces with this 4, makes it a 2. So I have 9 times negative 2, so that's negative 18. X squared times x is x cubed, and we have that over, I'm going to write it as 9x to the 4th minus 1 to the 3 halves. All right. All right, so in here, we needed to figure out the triangle anyway, right? But I'm going to do it again just by first changing it using the properties of triangles, all right? So this is going to be the same exact problem, but an alternate version of solving it. So I'll do it all in yellow. So this is I star. So again, I'm going to start with first figuring out the triangle. All right. Now we already figured out the triangle. So in here, we can just say that if I let theta be equal to cosecant inverse of 3x squared, well, then cosecant theta was just 3x squared, which told us that sine theta was 1 over 3x squared, right? And SOHCAHTOA, opposite hypotenuse, meaning that the remaining side, well, we found that to be 9x to the 4th minus 1, right, from the Pythagorean theorem. All right, so now tangent of that. Well, tangent is opposite over adjacent, opposite over adjacent. So in here, tangent of that angle, tangent of that theta, right, opposite over adjacent, so 1 over, and I'll write this as 9x to the 4th minus 1 to the 1/2, which I'll rewrite here as 9x to the 4th minus 1 to the negative 1/2. All right. So now, let's figure out f prime now. Well, let's rewrite f, right? So this was f, right? So what we said here is that f of x was tangent of this stuff. We just found that to be 9x to the 4th minus 1 to the negative 1/2. Okay, now let's find f prime based off of that. Right, so f prime of x would be negative 1/2 times 9x to the 4th minus 1 to the, subtract 1 from the exponent, negative 3/2 times the derivative of the inside. Well, 9 times 4 is 36, right? And then this negative, this 2, this 36, well, the 2 becomes a 1, the 36 becomes an 18, so I end up with negative 18x cubed over 9x to the 4th minus 1 to the 3/2. And that's exactly what I had up here, right? So whichever method you like better, I'm not going to force you to do one over the other. All right, so I'll do just one more example before I call it an end to this section. So that was example I. So example J. So let's say I have y is equal to 8 arcsine of x over 4 minus x times the square root of 16 minus x squared over 2. All right. So let's see what we can do here. All right. I'm going to rewrite this a little bit. All right. I'm going to rewrite this a little bit just so that we can work a little bit easier with this. So I'm not going to worry about this first part over here, that 8 arcsine of x over 4. I'm going to say that remains the same. But now I'm going to manipulate this statement right here. So let's look at how I'm going to manipulate that. So I have x times the square root of 16 minus x squared. All right. The first thing I'm going to do here is this over 2. I'm going to put it all the way out here. 1/2 times all of that. Now let's look at this x. X is the same thing as saying the square root of x squared. Otherwise, I could think of it also as x squared to the 1/2. And over here I have 16 minus x squared to the 1/2. And now that these are both to the 1/2, I can throw that inside there. All right. So when we do that, well, what do we get? I end up with, well, this 1/2 still out here, but I end up with 16x squared minus x to the 4th and all of this to the 1/2. All right. So that's what we get for this statement. So I'm going to write it as 1/2. Well, I'll write it in weight though. 1/2 times 16x squared minus x to the 4th to the 1/2. And the reason I wanted to manipulate that was because otherwise I would have needed a product rule here, and that might have been annoying to do, a product rule. So I changed this so that I only need to do the chain rule. All right. So let's go ahead and find the derivative here. Well, okay. So the derivative of arcsine. So we have dy dx is equal to 8 times the derivative of arcsine was 1 over the square root of 1 minus u squared. So x over 4 squared. Right, that's 1 minus u squared. Times the derivative of the inside. The derivative of x over 4 is just 1 over 4. Right? Minus the derivative of this. Well, this 1/2 is still there. 1/2 times the derivative of something to the 1/2 is 1/2 times that something to the negative 1/2, and that something was 16x squared minus x to the 4th. And then by the chain rule times the derivative of the inside, so times 32x minus 4x to the 3rd. All right. So let's see what we have here now. 8 times 1/4. 8 times 1/4 is just 2, right? So I have 2 over the square root of, this is 1 minus x squared over 16. And we have this minus, well, 1/2 times 1/2 is 1/4. And over here we can rewrite this as 32x minus 4x cubed over 16x squared minus x to the 4th to the 1/2. All right, so now let's manipulate this more. All right, there's going to be a lot of manipulation that we can do here. In this first radical here, we can come up with a common denominator, right? So this becomes 2 over the square root of, the common denominator here is going to be 16. So let's write it this way. Let's write it as something to the 1/2. And the common denominator is going to be 16. So this becomes 16 minus x squared. Minus. Up here, I see that I can factor some stuff out. I can factor out a 4x. So if I factor out a 4x on the top, I'm left with 8 minus x squared, right? And on the bottom, I still have this 4. But inside here, I see that I can factor out an x squared, right? Just like I was able to throw that x squared inside, I'm going to factor it out. So I have x squared times 16 minus x squared, and all of this to the 1/2, right? Perhaps I'll make this a little bit clearer, that these are all being raised to the power of 1/2. All right. Now, in here, in this first one, I've got this fraction raised to the 1/2. So what I really have here is 2 over, well, 16 minus x squared to the 1/2 over 16 to the 1/2, which is 4. All right, we'll deal with this in a second. Let's see what we can do over here. Well, these 4's reduce. All right, this x squared to the 1/2, right? Let me show you what happens here at the bottom. X squared to the 1/2 is just x, and then we have times 16 minus x squared to the 1/2. So this 1/2 applies to both here and here. But then we have, so that's this part in blue. But now we have this x and this x canceling each other out. So what I really have on top here is just, well, the 4's cancel out, so I just have 8 minus x squared over 16 minus x squared to the 1/2. Now let's think about this first fraction over here. I have a fraction being divided by another fraction, right? So I have 2 divided by this thing. So dividing by a fraction is multiplying by the reciprocal. So here I have 2 times 4 over 60 minus x squared to the 1/2, right? Minus 8 minus x squared over 60 minus x squared to the 1/2. Notice that both of these have the same denominator, 60 minus x squared to the 1/2. This first part becomes, well, 2 times 4 is 8. The second part, distribute this negative, so I end up with minus 8 plus x squared. So my final answer here is going to be just simply x squared over 60 minus x squared to the 1/2. All right. So, I mean, a lot of algebra in the middle to be done there, but the derivative of that function looks quite simple. All right, that is the end of 3.6. Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.